Hi, I am Brian, and I will introduce you our paper Exact-NeRF, an exploration of a precise volumetric parameterization for neural radiance fields or NeRFs. Our work is motivated by the gains in accuracy of Mip-NeRF when compared to the original implementation of NeRF. In its original form, NeRF performs a color and density estimation of points sampled around a ray that passes through the center of a pixel. These points are transformed using a position encoding function, which is a composition of sines and cosines at different frequencies to induce higher frequencies. However, this strategy can raise ambiguities that ultimately lead to blurring and aliasing. In order to reduce this, Mip-NeRF performs a volumetric position encoding by considering a cone that passes through a pixel and samples cone frustrums instead of points. Mip-NeRF defines an integrated position encoding that is the integral of the positional encoding function over the cone frustrum divided by the volume of that region. This formula has no closed form solution, so it is estimated using a fitted 3D Gaussian. With this implementation, Mip-NeRF prevents aliasing and reduces blurring. However, the Gaussian approximation degrades for larger regions, which are located far away from the camera. This is usually not a problem for bounded scenes, but it can be for larger scenes such as 360-degree photographic scenes that have a background, such as Mip-NeRF 360 dataset. For this reason, we introduced Exact-NeRF, which replaces a cone frustrum by a pyramid that passes through the corner of a pixel. Our research question is then if this change in the parameterization would enable an analytical and exact solution, and how this implementation compares with Mip-NeRF. In order to calculate an exact integrated positional encoding, we transform the volumetric integrals to surface integrals by using the divergence theorem. Now we focus on finding different functions f that are suitable for our problem. For instance, the denominator, which is in fact the volume of the pyramidal frustrum, can be obtained by choosing this function. Then, using the divergence theorem, we can obtain the following surface integral. By analyzing the shape of the pyramidal frustrums, we can divide the faces in triangles without losing generality, where each point here, p tau, it's one of the vertices for the triangle, and end tau is the normal vector, unit vector of the triangular face. Then, by using these coordinates and these normal vectors, we can obtain the following expression of the volume. This is a well-known formula for the volume of a parallelepiped. We can use the same strategy with the following function for the numerator of the exact integrated position encoding. This function is valid for the x-coordinate and the sine function of the position encoding in NeRF, but a similar analysis can be done for other coordinates and the cosine part of the position encoding. The final formula of the numerator is given by the following expression, where xk is the kth coordinate, 2 to the O is the frequency of the position encoding, and capital X tau here, it's a matrix containing the coordinates of the vertices of the triangle. It is worth noting that this formula is valid for any parallelepiped shape and not only for pyramidal frustrums. This fact is exploited by the implemented Exact-NeRF in the Mip-NeRF 360 context that performs a contraction of the space. This contraction will ultimately lead to a deformed pyramidal frustrum that can be still calculated using our exact integrated position encoding. By comparing Exact-NeRF with Mip-NeRF in the Blender dataset, it can be observed that their constructions are quite similar, with slight improvement of the perceptual metrics LPIPs and DISTs. However, more significant differences can be observed in Exact-NeRF against Mip-NeRF 360. As noted earlier, our method can be applied to Mip-NeRF 360 for unbounded 360-degree scenes. Although our method has a slight decrease in performance, it is still competent. It also shows some interesting qualitative results. For instance, our method is prone to error for tiny vessels that are close to the camera, as in the bicycle cable here. However, it exhibits a significant improvement on distant objects such as the cleaner reconstruction of the grill and the car in the bicycle scene here, you can see there are some artifacts here in the Mip-NeRF 360 that are not observed in Exact-NeRF, and also in the background reconstruction of the garden scene of Mip-NeRF 360 here, where we can see that these sticks are better reconstructed than Mip-NeRF 360. There are some gains in the background regions of the depth estimations. The previous car and glue reconstructions of the bicycle scene are cleaner for Exact-NeRF in the depth map, that we can see here and other regions as well. In the bonsai scene, some improvements are noted in the wide supporting pole, which is here. This is Mip-NeRF and this is Exact-NeRF. In the back of the chair and in the window area. Similarly, there are several objects in the background of the garden scene that are reconstructed better with our approach, which is the same scene as shown in the previous example. Our method is prone to numerical underflow, given some small numbers in the numerator of the exact integrated position encoding. The following image shows an example of these regions showing the numerical underflow, which happen to be where two coordinates are very close. The curvature of these regions is a footprint of the contraction function of Mip-NeRF 360. These artifacts can be mitigated using L'Hopital's rule. This calculation is detailed in the supplementary material of our paper. In conclusion, Exact-NeRF is an alternative exact parameterization of the volumetric position encoding of Mip-NeRF that uses pyramids instead of cones. We were able to show that our approach has a similar performance compared to Mip-NeRF 360. With Mip-NeRF and Mip-NeRF 360, and it can be implemented right off the shelf in Mip-NeRF 360. Exact-NeRF shows a better reconstruction of background objects. This indicates that a hybrid implementation of Mip-NeRF in nearby instances and Exact-NeRF in far objects might be ideal. The key idea of Exact-NeRF can be exploited in different applications and not only in NeRF itself. It also enables future exploration of new positional encodings. Thank you very much.